Good morning. I am Prasannanjaneya Reddy, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. In this session, we are going to discuss about task synchronization. For this topic, we can follow the textbook is Introduction to Embedded Systems by Shibu KV. Task synchronization means in our device, in any embedded systems, we are doing different types of operations, playing the music or open the door, open the airbags, like that. At the same time, behind these operations, different types of process is executing. While executing, one process may interact with the other process. The communication is called inter-process communication. While providing the communication among multiple processes, they require some resources. Otherwise, let us consider process P1, process P2. Suppose one operation is divided into different types of processes. Open the airbag. Open the airbags contains different types of process internally. Okay, process P1, P2, P3, P4. This process P1 may require the data from P2, or the process P1 may require the input port or output port, or some additional hardware circuits, or some display devices, or some actuators at the same time. If multiple processes need more than one resource at a time, how we can provide the resources to the process? That will be discussed in this session. That is task synchronization. In a multitasking environment, multitasking means more than one task is executing at a time. So multiple processes run concurrently, means parallelly, and share the system resources like display panel or additional hardware or communication peripheral or some communication buses, like that. Apart from this, each process has its own boundary wall and they communicate with each other with different inter-process communication methods, including shared memory or message passing, remote procedure call, anything, any one of them, it will use that one for sharing the information. Imagine a situation when two processes try to access the display hardware connected to the system, or two processes are trying to access shared memory area. When one process wants to write the data, another process wants to read the data from the same memory location. So what could be the result in these scenarios? What happened? What is the result? Obviously, we are getting unexpected results. So to address these issues, we are going for task synchronization. The act of making process aware of the access of shared resources by each process to avoid conflicts is known as task synchronization. Means each one knows the awareness, which one is highest priority. Based on the priority, that process access the resources or get the resources. So that rules and regulations are the priorities are that will be defined here. First, which process access the display device. First, which process access the memory device. If at the same time these two processes require that resources. Various synchronization issues may arise in a multitasking environment if processes are not synchronized properly. So here we are discussing here to overcome these issues. So different types of issues arises while executing multiple processes which are requires same resource, either shared memory, either display devices, and so on. First one is racing, deadlock, the dining philosopher problem, producer, consumer or bounded buffer problem, reader, writer problem, and priority inversion. We will check one by one. Racing. Racing means here we are consider two processes. Process A. So we are defining process A. That doing some increment operation. At the time, process B doing some increment operation here. Further, we are taking some buffer. Initially, buffer is 0. The buffer size is, we are considering here 10. Okay. So, process A doing increment operation, process B doing increment operations. If they are doing same operations at the same time, okay, for a programmer point of view, the value of the counter will be 10 at the end of the execution of a processes A and B. But it need not be always in a real-time mode execution of this piece of code under a multitasking kernel. The results depends on the process scheduling algorithms adopted by the OS kernel. The program statement counters ++ means increment operation looks like a single statement from high level language point of view. In C language point of view, it indicating adding some 1, A plus 1, A equal to A plus 1. But coming to the assembly level language, it internally doing 3 operations. If you look at this one, first we are loading some memory location content into the accumulator, then increment the accumulator by 1, then the incremented value is loading into some memory location. Okay. Internally, the increment operator doing these 3 operations. This is assembly language level. This counter ++ is high level language, that is C language. Okay. So, whenever these two context switching happens, means preemption happens. So, at the processor instruction level, the value of the variable counter is loading with the accumulator value. The memory variable counter is represented using a pointer. The base pointer register is used for pointing the memory value counter. After loading the content of the variable count to the accumulator content is incremented by 1 using add instruction. Finally, the accumulator is loading to the memory location that is defined here. Both the process A and B contains increment operation. If you translate these two operations into the machine level, we are getting these instructions in assembly level language. Here, loading the memory location value into the accumulator, increment the accumulator by 1 value, and incremented value is loading into another memory location. Same operation doing here for process A, process B. So imagine a situation where a process switching happens from A to B. When A is executing increment operation like that. Just imagine process A doing increment operation at that time. If any preemption happens, what happens? Now imagine the process switching happens at the point where A executing the low level instruction is move EAX memory location value and is about to execute the add instruction. It is loading the memory location value to the accumulator and the next one is adding the 1. At this point of time, if switching happens means okay. So at that time process B value is loading into the accumulator, the value may be mismatches and we are getting wrong results. So the variable counter is incremented by process B. Process A is unaware of it and it increments the variable with old value. This leads to loss of increment for the variable counter. This problem occurs due to non-atomic operations on variables. This issue would not have been occurred if underlying actions corresponding to the program statement counter plus plus is finished in a single CPU execution. If it happens in single clock cycle, that is not a problem. But if you are taking more than one clock cycles, at the time of another clock cycle, if switching happens means it may do the wrong operations and leads to wrong results. We are getting undesired responses. The best way to avoid the situation to make this access and modification of shared value is mutually exclusive. Meaning, when one process accesses a shared variable, prevent other process from accessing it. One person utilizing the services, stop the another person to access that one. That's the only possible solution to avoid conflicts. So to summarize, this racing or race condition is a situation in which multiple processes compete each other to access the same resource, manipulate the shared data concurrently. In racing condition, the final value of the shared data depends on the process which acted on the data finally. So what is the decision we are taking here? Based on that, we are getting the response, either positive or negative. So next, deadlock condition. So the result of the race condition, deadlock occurs. Means, if you look at the traffic signals, here 4 sides are there. At this particular point of time, all vehicles are moving towards the junction means so everything will be stuck here. It is not possible to cross the junction by the vehicles. Okay, that is, so no vehicle will cross the junction. So that is called deadlock condition. Because of racing, the deadlock occurs. To avoid the situation, we can stop the vehicles and come back in one direction, allow the vehicles in another opposite side vehicles. Stop the vehicle in one direction, allow the vehicle in the opposite direction, then the traffic is cleared. In its simplest form, deadlock is the condition in which a process is waiting for a resource held by another process which is waiting for the resource held by the first process. Means, one process utilizing the resources, another process waiting for the same resource. To elaborate, process A holds the resource X, process and it wants to resource Y. So see this image, process A, process B, two processes are there. Process A wants X, process B wants Y. If process A wants to release the value, X value, it must complete this operation by utilizing this Y. If Y releases, process A operation completed, then only X will be released. If both are holding, if no process is not releasing anything, the operation is stopped. No process will be executed. So the different conditions favoring the deadlock situation are listed below. One is mutual exclusion, means internal change. So if any one process release the resource means another process complete its operation and release the desired source to the other process. Next one, hold and wait. So whenever a process wants other resources, by waiting, by stop that one and wait for until getting the resources. And no resource preemption means here the criteria that the operating system cannot take back a resource from a process which is currently holding it, and the resource can only be released voluntarily by the process. It is not possible to return back the resources by the design. The process voluntarily release the resource, then only another process get the resource. That is no resource preemption. It is not possible to return back the assigned resources until the process voluntarily release the resources. Circular wait. Suppose process 1, process 2, process 3, process 4. We are considering 4 processes. Process 1 requires process 4 to complete its operation. Okay. But 4 requires 3 resource. Process 4 requires the resource from process 3. Process 3 requires the resource from process 2. Process 2 requires the resource from process 1. So each process depends on other process. But at a time, if all resources are looking for resource means it is not possible to get the response. That is called circular wait. Next, deadlock handling means a smart OS may foresee the deadlock condition and will act proactively to avoid such a situation. Means it will estimate the what are the possibilities to get the deadlock conditions in this desired OS. Now, if a deadlock occurred, how the OS respond to it? That depends on the design of the operating system kernel. The reaction to deadlock condition by the OS is non-uniform. It may be varies. The OS may adopt any of the following techniques to detect and prevent deadlock condition. Those are: ignore the deadlocks. While designing the operating system, we think that no deadlocks are there. Example, Unix. Otherwise, if you are thinking something happened like that in coming days, we can't design that one. The cost of the design is more. That's why we imagine that OS designing is deadlock free. That's why we are considering ignore deadlocks. Detect and recover. If any deadlock occur, we need to identify that one. This approach suggests that the detection of a deadlock situation and recovery from it. This is similar to the deadlock condition that may arise at a traffic junction, traffic signals. Okay, in traffic signals, in all directions if the vehicles coming at a time means the traffic jam occurs. To avoid that one, stop the vehicles in 3 directions and allow in 1 direction only. In case of 4 directions are there. Operating system keep a resource graph in their memory. The resource graph is updated on each resource request release. Here resource graph means the resources is held by the particular it contains the details means which resource is held by which process. Suppose if any new process wants particular resource, at that time it will check that resource is available or held by any process. That up to date list is available in the memory. So each time the operating system update that resource graph and release the resources based on the requests. Next, avoid deadlocks. Deadlock is avoided by careful resource allocation techniques by the operating system. If you are efficiently assigning the resources means deadlock not occurred. It is similar to the traffic light mechanism at a junctions to avoid traffic jams. Prevent deadlocks. Prevent deadlock condition by negating one of 4 conditions favoring the deadlock situations. Those are: ensure that a process does not hold any resources when it requires a resource. That completion of resources, it takes somewhat time. If any process send a request and the requested process is taking time to provide that one means release the resources from that process. Suppose process P1 is there. Process P1 requires some resource X. If process P1 takes some time to get this resource X, at that time, whatever the resources held by process P1 that needs to be released. Otherwise, whatever the time it is waiting for getting the X is waiting here. That is avoiding deadlocks. One of the point. That is one of the point. Next point is a process must request all its required resource, and the resources should be allocated before process begins its execution. Suppose if any new process is starting its execution, process P1, it sends the list of resources required. What are the list of resources required for doing its operation? That is one of the point. Next, grant the resources request from process only if the process does not hold any resource currently. So, assign the resources. Okay. Release all the resources like this. So, live lock means, so one of the simple solution is, it is similar to deadlock. Live lock is similar to deadlock, except that a process in live lock condition changes its state with time. In deadlock, no process will be executed. In live lock, the state will be changes with respect to time. While in deadlock, a process enter in wait state for a resource and continue in that state forever without making any progress in the execution. In a live lock condition, a process always does something but is unable to make any progress in the execution completion. So the live lock condition is better explained with real-time example. Two people attempting to cross each other in a narrow row. Suppose it is narrow row. Process P1 is coming in this direction. Process P2 coming in this direction. But here it is not possible to cross one by another. Process P1 moves in this direction, process P2 moves in the direction, opposite direction. Moving is possible, but crossing is not possible. That is live lock. In case of deadlock, moving also not possible. Both the persons move towards each side of the corridor to allow the opposite person to cross. Since the corridor is narrow, none of them are able to cross each other. None of them are able to cross each other. Here both of the persons perform same action, but still they are unable to achieve their target. Cross each other. They are unable to cross each other. Task synchronization issues. One is deadlock, and that starvation is there. In the multitasking context, starvation is the condition in which a process does not get the resources required to continue its execution for a long time. Okay, that is called starvation. As time progresses, the process starves on the resource. Starvation may arise due to various conditions like byproduct of preventive measures of deadlock, scheduling policies favoring high priority tasks, and tasks with shortest execution time extra. Suppose process P1, process P2, process P3 are there. Process 1 P1 is scheduled for execution, means running state. At that time, if P2 and P3 is coming at the beginning itself, but because of highest priority of other process, it is preempted. Or because of lowest execution time of P2 when comparing with P2. P2 is always stopped because of lowest priority or highest execution time. Because of that reason, the P2 is scheduled for execution takes much time, even that is coming at the beginning of the execution. That is called starvation. To prevent this, we can dynamically change the priorities of the scheduling process. So, another one is dining philosopher problem. Means, suppose we are considering 5 persons. 1, 2, 3, 4, 5. We have 5 forks. 4, 1, 2, 3, 4, 5. If they want to eat the dinner means they require 2 forks, but they have only 1 fork. How it is possible to complete this dining? Means completion of dinner means the particular person waiting for another person to get the fork. Whenever he keep the fork down, Then only whenever another person, suppose person 1 having one fork by default, if he wants another fork means whenever person 2 or person 5 down the fork, whenever he completes his dinner and keep the down the fork, then only person 1 get the fork. Otherwise, no one are unable to eat the dinner. Okay, so that's the only solution. So one person, we can schedule that one. We can give time slots for first person first slot, second person second slot, like that. Then that is the solution only to avoid these issues. At the same time, if the two persons are having same resource means we are assigning time slots. First person utilizing that resource in the first slot, second person utilizing resource in the next slot, like that. Priority inverse means dynamically we can change the priorities based on the requirement. If any highest priority task is coming to the for execution, stop the current execution and execute the highest priority. In some cases, some highest priority task may require the resources from lowest priority task, but lowest priority is not executed because of scheduling or highest priority scheduling algorithm. At that time, we can change the priority of highest priority of the task to lowest priority priority of the task priority to the highest priority. So, two process P1 and P2. This priority is 1, this priority 2. We are executing process P1 because of its highest priority. Suppose P1 requires the resource from P2, it is not getting resource from P2 because it is lowest priority. So we can change these priorities, low to high, high to low. That is priority inversion. That will happen dynamically. We can solve this issue. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.